So we're going to start by going over the homework from yesterday, and I'm going to, this is one of those questions that it says suggest, and that's always both nerve-wracking but also kind of freeing, okay, when that's your command term is suggest, because you need to, they're going to have a list of possible answers that would be acceptable, and you just need to be somewhere on that list. So it's not like there's just one right answer for a suggest question. But you also have to kind of, usually the questions are a little bit more thought-provoking. It's not something that you can just be like, oh, I had that memorized, right? So it's the good and the bad about suggest. So looking at this, this diagram of energy levels, this model of electron energy levels, what are some limitations to this that you guys came up with? Jocelyn.
You don't know the exact energy.
Okay. Okay, what else? Yeah, January.
You can't show movement between orbitals in the same energy level.
Okay. Anyone come up with anything else? Yeah, Finn? Oh, okay. Anything else? So I'm gonna put up the mark scheme, okay, so that you can see all of the things that they thought would possibly be acceptable. Notice that it does say 2 limitations. So, and there's 2 points. So, as always, check the point levels on the questions, because if it's 2 points, there are 2 points they want you to make. Now here it actually said suggest 2 limitations. But even if it just said suggest limitations, but it was 2 points, that probably means they want you to put 2 things together. And if you only think of one, write the one, because that's one of the points. So, don't cheat yourself because you can't think of 2, but realize that that's what's happening. Okay, so here is the mark scheme, and it says any 2 out of all of these. So doesn't represent sublevels orbitals. Yep, we got that. Only applies to atoms with 1 electron, or only applies to hydrogen. Okay, it does not. That particular sort of model of the hydrogen atom doesn't work if we're talking about iron. I mean, it does, but it's not in the same way, okay? And remember, I think I mentioned this, that when Bohr figured out all the math and did all his calculations, it worked great for hydrogen, and then he tried to apply those to helium, and it didn't work because he had to bring in Schrodinger and other stuff about quantum mechanics in order for it to get the math working. So there is math that does that, but it's more complicated than what he sort of started with. Doesn't explain why only certain energy levels are allowed. Okay, so why is there not a continuous emission spectrum, for example? Why are they only why are only certain places allowed? Sorry. We're assuming that the atom is all by itself and there's no bonding electrons playing a role here, that it's not an ion. So, there's a lot of things that get more complicated when we start talking about more than one atom. Same idea doesn't take into account interactions between atoms or molecules. Doesn't consider the number of electrons that any given energy level can fit. So energy level 1 only fits 2, etc. So that's not included in that model. Or really thinking about it in terms of probability of finding an electron, rather than thinking about it as, in the Bohr model, sort of distinct levels as if they were places where the electron would go. So any of those things would have been acceptable. Sometimes what the mark scheme will say is they'll say do not accept a particular thing, because usually it's either something that they think is obvious and isn't actually you thinking about a suggestion, or it could be a common misconception that people write about a lot when they answer these kinds of questions. So sometimes, in this case, it says do not accept does not represent distance from nucleus. Okay? So we talk about the energy levels as if the nucleus is at the bottom of that screen, right? And it is a good model of how to think about it, but it doesn't exactly work that way. But they don't want that to be the issue. They want like this whole model of having energy levels. That's kind of what they're looking for than whether or not it specifically represents a particular distance from the nucleus. I don't know why they won't accept that, but they might accept other things. You'll notice that there's this. If you read through a mark scheme, there's the OWTTE. That's other words to that effect. So you don't have to have those exact words, or as long as the same concept comes around, then you get the mark. If you said something that was not on this list, but also not on the do not accept section, would they give you the point? What I have been told is that the moderators are looking to give you points. So if there's something that was maybe not on this list but made sense, I think they would give you the point. But I've never been a moderator, so can't tell for sure. They really do like limitations of models, limitations of experimental design, things like that. That comes up a lot. Maybe I will see if I can find more questions like that. So you can see other examples that maybe we haven't run across in the test questions that you've seen so far. Any questions on that one? Okay, the arrows should have been in these places. I want to note that the first arrow that they ask for, and just ignore these numbers because it's numbered differently in the question bank, but in the first case it says draw an arrow to represent the electron transition for the ionization of a hydrogen atom in the ground state. So this one specifically needed you to go from n equals 1 to n equals infinity with an up arrow, okay, to show that you're increasing the energy of the electron. Interestingly, the second one says draw an arrow labeled Z to represent the lowest electron transition in the visible spectrum, okay? So in the visible spectrum, it needs to be going towards n equals 2, right? So this is where we get visible light. But they point out in the mark scheme, you could have an upward arrow because it says transition. It doesn't say emission or absorption or increase or decrease in energy. It just says transmission. So you could have drawn an arrow like that. That would have been fine too. Yes. It would, so anything coming down to n equals 2, that's where the visible ones are. So the ones going all the way down to n equals 1 are going to be in the ultraviolet. Ones going to n equals 3 are going to be in the infrared. The visible spectrum, all of those lines come from electrons transitioning down to energy level 2. And in terms of the fact that it says the lowest energy electron transition, that's going to be the smallest drop, right? What color is that line going to be? for the smallest visible transition? Ella? Red, yep. So this is going to be the red line that you see, because remember, red is longer wavelength, closer to the 700 side of the visible spectrum, less energy, okay? The next line, I don't think they will, I haven't seen one where they ask you the color, I don't think, but given that they asked for the lowest energy, like they could totally ask you the color, because that is the one part of a spectrum for an element that you are required to know is visible hydrogen, okay? So that, like the n equals 4, I don't really have a teal option here, but this would be sort of blue, teal, and then n equals 5 would actually be, more blue or violet. N equals 6 would be violet. Yeah. But so if it says transition and it doesn't specify that it's going one way or another, you can put the arrow either way. But look for those specific words in the question. So ionization, ground state, that tells us that it's got to be going up, and it's got to be going up from n equals 1. Okay. And the last one was asking for an energy difference. Notice that this is not asking for ionization energy, which is what we've been calculating in class. It's asking for an energy difference between sublevels within the third energy level in a sodium atom. Okay, so now we're starting to get into, this would be related to the flame test. Okay, why is sodium yellow-orange in the flame test? Well, because the wavelength that is associated with this frequency is that in that range. Okay, so you're not required to know that, but all you need to realize is that calculating the energy difference is exactly the same way you've been calculating the ionization energies. You've got frequency, and and so you can use your E equals HF because you're being given that frequency, right? So I think, yeah. So for something like a calculation, usually they will just sort of give, sometimes they'll give alternate methods of doing a calculation if it's like a stoichiometry multi-part kind of thing. But basically it's saying, okay, it's H, well, here's a nu, which is the same as an F, where we're taking Planck's constant and we're multiplying it by the frequency. One thing that you'll see these double angled brackets, and that's kind of another way of saying something that looks kind of like this, even if it's not written in exactly this format, and then also in the double brackets is the unit. So hopefully you put the unit of joules in your answer. Now, you could have converted this to kilojoules and given the correct answer in kilojoules if you divided it by 1,000, right? So that's kind of why the J is in the brackets, because it's like, well, probably joules, but if you did it in some other version of joules, then that would also still be correct, right? So hopefully you got something close to 3.37 times 10 to the negative 19th joules, okay? And notice that it says joules in joules, so it doesn't say kilojoules per mole, right? So pay attention to that, because you did not need to and should not have multiplied by Avogadro's number in this case, because it was just asking for it in joules, even though one of the practice questions we worked on yesterday was asking you to do that, to convert it to kilojoules per mole. That's not what we're doing here. Yes? You could, because it's the same unit, it's just a different power of 10. Yeah. So So if it asks for, yeah, if it says joules, I think you could do it in kilojoules. Generally speaking, you want to do specifically whatever it asks for. So I would say probably, I mean, I would give it to you if it was the right power of 10 and kilojoules. The idea is like that's the unit that you're using, but I could be wrong about that. They might actually only want joules, in which case I don't know why this is in the brackets. Yeah. Yeah, you would have to do that. You're right. You're right. So maybe I'm wrong about that. So I'm not really sure why the bracket. Yeah. Yeah. Yeah, I don't know. That's a good point. Yeah, probably they want it specifically in joules if they said they want it in joules. If they didn't specify, if they just said energy difference, then you could do either one. Yeah. I mean, you could put it in megajoules if you really wanted to, but like that, you know, we don't. I would try to keep it to things that we normally calculate in, or that you've seen questions from that range. Okay. So I'm about to give you some practice questions on the stuff that we talked about yesterday, the sequential or successive ionization energies. So there are just 3 questions. The third one might be a little bit, you might have to think about a little bit more than usual. Mm-hmm.
Why is it big?
Okay. So I'm going to give you guys some time to work on these, and then we will go over them. So maybe about 10 minutes, or I'll just look around and see if it's taking shorter or longer. Your next assignment outside of the lab is to do a study guide for 1.3 and 1.3 HL, because we're done with 1.3. Okay. I will not make that due probably. Definitely not before next Friday. Do you guys want like a full week? Because we'll also be doing the lab and stuff. Because I can make it the following Monday. Do then. All right, I'm gonna shut this down.